In today's TTED 4035 lesson, where we're taking a look at printed circuit board design, we're going to be looking at using multiple layers on the circuit board and how to fake that when you can only make a single layer board. And the board that we're going to design to do that is a 7-segment display shield for your Arduino. So I thought we'd come to Tinkercad and just take a look at what a 7-segment display was and some of the terminology before we started designing the board. So here's a basic screen in Tinkercad. We've got our Arduino hooked up right here to our breadboard. We're not going to use the Arduino for anything right now, although in a future lesson we may take a look at that. What I just wanted to take a look at right here was this 7-segment display. It should be fairly familiar to anyone who's ever used a calculator or looked at an alarm clock. And it's called a 7-segment display because you have 7 segments in your LED. Right along the top is 1, 2, 3, 4, 5, 6, 7, along with an eighth for your decimal point. But there's 7 segments around here. Each one of them is an LED that will light up. They have different names. So instead of simply calling them 1 through 7, this is A, B, C, D, E, F, and G, and the decimal is often known as D or DP when you look at the schematic diagram for it. So when we take a look at our pins on here, you'll see that it has a common, and that shows up as red. So what this is telling us is that this is a common anode 7-segment display, which means that we provide 5 volts or whatever voltage our power supply is going to be, but typically 5. We supply 5 volts to the 7-segment display. And this one actually has 2 common anode pins, one at the top and one down here at the bottom. Now, it also has pins for segment A, so when that pin goes low, segment A will turn on, B, the decimal point, C. Again, this is our common anode. We could supply power here, or we can supply power there. You can choose either one. You don't have to do both. D, E, F, and G. So let's take a look at what happens when we run this simulation right now. We have segment A turned on because we have 5 volts coming in here on our positive line. I could have just as easily hooked it up down here onto this common anode. I only need one of those 2 to be hooked up. And so I come in here and I'm hooking this up right here, and A then is grounded right through here. So A is getting power across of it, and so segment A turns on. If I move my resistor over one hole and start the simulation, you can see that segment B turns on. And if I stop that and bring it down here, the decimal point, and this right here says it's segment C, so A, B, C. The next one would be D. Now keep in mind that's going to be our common anode. That won't do anything to us. But start simulation. There is segment D, segment E. Up here is segment F. And just to wrap it all up, segment G. Okay, so now that's what we can do with one 7-segment display. Typically what you'd see on a 7-segment display is you'd have multiple 7-segment displays put in side by side. And each of them would have resistors coming to each of their pins right here and going back to your Arduino or microcontroller so that you could turn on the individual segments when you wanted that to light up. Now, if you started adding multiple segments, multiple displays, all of a sudden you would very quickly run out of pins on your Arduino because to manage 7 segments plus the decimal point requires 8 pins. So the Arduinos use a really cool trick known as multiplexing, where they only turn one of the displays on at a time. They just flicker between them so fast that the human eye can't tell that they're turning them on and off really quickly. So in a 4 decimal 7-segment display, only one of the LEDs, only one of the seven segment displays is activated or turned on at a time, the Arduino is just cycling through them really, really quickly. And there's some libraries available that you can get to do that, or you can write your own code to manage it. And like I say, we'll take a look at the code on a future day, but I just wanted to take a moment to take a look at the seven segment display. You can have multiple segments turned on. So if you wanted the number 1 to be displayed, you would turn on A and B. Oops, sorry, you would turn on B and, don't do that right there. You would turn on B and C, and there the number 1 is displayed on your display. And if you wanted the number 7 to be displayed on there, then you would turn on A, B, and C. And then you've got the number 7, and obviously if you turn all the 8 segments on, you get the number 8 being displayed on your 7 segment display. So it's a neat way to display things, and when you get used to the concepts of how a 7 segment display works, you can actually scale this up, and instead of just using a single LED to make a segment right here, you can take some LED strips and you can make a larger signboard, put some really bright LED strips right in here, and you can actually have a display that's visible outdoors in bright light and hook it up to run off of 12 volts and have the Arduino use a transistor to. Am I getting ahead of things? Anyway, once you understand how a 7-segment display works, you can do some neat things with it. But we're going to take this concept of the 7-segment display and use it to make our shield today. And we're going to take a look at some of the techniques that you can do, both to make the board route a little bit easier and how you can save yourself a little bit of hassle when it comes time to route things. So let's go over to Fusion 360 and move into our electronics design components of Fusion 360. Okay, so make sure that you're in your correct folder. If you've been working on a library, that might be visible in your project box right here. And what we're going to do is we are going to come in here and we are going to create a new electronics design. And we are going to call that the 7-segment shield. So go ahead and save it right here. So this is your project, and 7-segment shield. And you can actually call it CA because we're going to be working with a common anode. Remember that we hooked up a positive power supply to our shield right there. So this is a common anode as opposed to a common cathode where the Arduino would provide power to each pins and your ground would sync that power. Here, the board is providing power to your display and the Arduino is syncing that power and turning things off that way. So when we've talked about RGB LEDs in the past, we've talked about common anode and common cathode, two different choices. You've got those same two choices with your 7-segment displays. This one, the common anode, or CA. Okay, 7-segment shield, common anode, and now it's time to create a new schematic. There we go. Let's save that as well so that when we get started, it's already saved. 7-segment CA. And maybe we should, 7-segment shield is what I called it. Let's just be consistent with our naming on there. Okay, you've got this saved. It's time to start designing a schematic. Now, we can clear out a little bit more space on the board. I don't need this displayed over here, so I can click that little arrow and that disappears. If I ever need that back, I can kick over here and that will pop on again. And I'm just going to keep this open for right now because we need to find some parts and we need to add them in from our libraries. So let's add the first part, and seeing as how we're going to make a shield for an Arduino, let's bring in an Arduino. And the Arduino is popular enough that it's actually a pretty standard part. So let's add a part right here. And earlier we added the Adafruit library to our project. Okay, now if you forgot what we did and you don't have the Adafruit library in there, okay, you can open the library manager and you can come in here, take a look at the available libraries. Okay, and there's a whole bunch of them. You can scroll through them And obviously that Adafruit library doesn't show up on mine because I've got it installed. Mine's in the in-use libraries, which means that I've downloaded it. But if you don't have an Adafruit library available, then you can come in here, you can click on this, and you can click on use, and next thing you know, you'll have the Adafruit library in your usable libraries. It'll be downloaded and copied to your system. And if you take a look in the Adafruit library, they've got a whole bunch of parts, many of which are a bit intimidating to the beginning circuit board designer. However, if you scroll down, you will come to a name that you recognize, and you've got the Arduino. Now, the Arduino has a couple of different little footprints that we can use right here. That one looks pretty standard. You can take a look at our different choices here. They all look pretty much the same. Oh, there are mounting holes on that one. And there's just your standard Arduino Uno. There's one without the mounting holes. There's one with the mounting holes. Not sure what they're missing with that one. The outline is on the dimension layer, so they've changed it around. So anyways, let's just use the Arduino Uno that they've got right in here for us. This is going to be a great library, or a great part. And there is our Arduino right there. It looks pretty familiar, and I can hit the escape key and get right out of there. So now I want to add another part, and I want to add a 7-segment display. So I don't want that from the Adafruit library. And this is one, if you don't quite know where to look, you can come in here and you can do a search. And so 7 didn't come up with anything. Segment, for some reason segment worked out. And if I take a look at this, that's why it showed up. It used the number 7 instead of the word 7 right in here. So just a couple things to think about when you're searching. Don't forget to use the number or the word. And you'll see that this one right in here is shorthand 7seg-CA. Okay, so common anode, common cathode right there. And if you click on it, there you can see this is the logical representation. The pins aren't in the exact same position that they're going to be on this chip. You'll recall, for instance, that our anode, one was right here and one was down here. On here, just because it's easier to display in the schematic, they're right next to each other. So this is good. This is one that we like. And this is a 13 millimeter high version, which is a pretty standard size for 7-segment displays. It's fairly small. You can actually buy them up to like 20 centimeters or larger. But by the time you're getting to that big, you're probably better off buying some LED strip and building your own if you're looking for a budget version. Okay, so you've got the 7seg-CA from the optoelectronic library that came installed with Fusion 360. And let's go OK and drop a 7-segment display right into here right now. There we go. So that's going to be our first digit in the 7-segment display. And let's click on OK. And we're going to start by just adding one segment right here. I'm going to show you a little bit about what we need to do to make that work and have it be happy. We're going to need some resistors to go with it. So come back to add part, and we've added resistors before. And you can just search for resist star, whatever you want to search for. You can just go look at them in the resistor folder. You may have a particular favorite folder to draw them from. Quite often I've been drawing from them either from the resistor or from the Adafruit library. Actually, I think the Adafruit library had the nicer selection of choices because it gives you the standard American symbol for a resistor, and you can then come down here and choose your size and your length. And I think pretty standard that we've been using is somewhere around the 03, 09 /12. So 12 millimeters from hole to hole right on here, and 3 millimeters by 9 millimeters across for the resistor. Pretty typical size. You can probably get away with a 0207 10 or 12 if you want to, but I think the 0309 12 is going to give us lots of space. Okay, there we go. So an 0309 12 part, and it's going to come right in here. And we're going to need a bunch of these. So I'm going to space them apart a little bit right in here. Now, to save a little bit of time, okay, I want them all to have the same value. So I'm just going to put one in there and I'm going to say, okay. Sorry, I'm going to cancel that, hit escape. And then I'm going to come in here and I'm going to change the value. And I'm going to set that value to 100. 100 ohms. Again, it's hard to find the ohm key on your keyboard, so we'll just say 100R right there. And then just to make it so we can fit things in a little more compactly, I have to hit escape so that I can move things around. I'm going to bring that 100R right up there, space that nicely right like that. So now I can take that part, I can go copy, and I can paste it down right there. Paste it right there. Paste it right there. How many do we have on this side? 1, 2, 3, 4, 5. So I've got 5 resistors right there. And then I'll put over on this side F, G, and the decimal point over here. And again, I'll just space that up a little bit. There we go. Everything seems to line up really nicely from the bottom right there. And we may have to space some things out on our Arduino just to make things stand out really nicely in there. Okay, so we've got 100 ohm resistors coming everywhere right in here. And now we can start hooking some of them up and just do the easy connections first. And taking care to space that out really nicely. If you need to take a moment to get that lined up nicely, go ahead and do that. You'll notice that I do have one little glitch right in here. I'm just going to take escape for a moment and move that 100R right off there. I didn't like having something written right over top of it. That wasn't good practice to have a line over top of the number right in there. I don't really like moving it down here when I've got kind of a standard arrangement right here. You could also just get rid of all these numbers and provide a note sheet saying R1 through R8 are all 100 ohm resistors. And quite frankly, the 100 ohm is not a particularly important value. You could put a 200 ohm resistor in there. LEDs would be slightly more dim. They would work perfectly fine. And you'd use less power from your Arduino too. Okay, so now let's come in here and hook this together. And there's our decimal point hooked up, our G hooked up, and our F hooked up. Okay, so I'm looking at now, how am I going to hook this easily up to the Arduino? Well, what's going to be the best arrangement right here? I think I'm going to take the Arduino, hit escape right here, and I have to click on that little, okay, hit escape, so I'm no longer drawing lines. And what I'd like to do is I'd like to rotate that. So I'm just going to click on that and go rotate. And I'll probably rotate it a bit more. And we can, come on, you, rotate. Okay, there we go. And now, as you can see, I don't want to rotate anymore. I'll drag that up here. I've got my numbers pointing out right down over this way. Life is good. Maybe I'll just move that up a little bit higher. Okay, now as far as hooking up my schematics right here, I'm going to go ahead and just loop them around like so. And I'm going to have D0 go to A, B, C, D all the way down there, and then E, F, and G. And then we'll talk about the common anode ones in just a moment. Before I go too much further into this, however, I would like to point out that although we're going to hook them up in a way that makes sense on the schematic, when it comes time to route them, what makes sense on the schematic doesn't always make sense on the printed circuit board, and you may want to come back and change some of these things a little bit later on. Actually, now that I think about it, I'm probably just going to move this right over here so it's a little more centered right on the top. Okay, so let's come along right here, and D0 is going to come down out here, and let's route this. And this is going to look nice and neat on our schematic. We do like to have nice, neat schematics. Now, there's a couple of things that I've done in here that, people could say aren't particularly great practice when working with the Arduino. One of which is that I'm using pins D0 and D1 when I probably don't really have to. And the only reason I say that I wouldn't necessarily use D0 and D1 is if you look at your Arduino, they have TX and RX stamped next to them, and that's your serial ports. So your serial port transmit and receive. So if you want to be able to communicate with a computer and do serial print or anything like that, using these ones is probably not a good idea. D2 and D3 are your external interrupts. So if you're planning to do anything with them later on, you probably don't want to use them here either. And then, of course, you've also got your PWM pins that you can do your direct analog writes from in here. But I'm not going to get too fussy about that for right now. I'm going to carry on right here, and this is looking reasonably pretty, so I'm just going to carry on with it. And so I'm going to come down right here and hook up. Right to there. So now I've got all my pins hooked up and tied back into the Arduino right here so that I can sync current from any of these pins. And if I set D4 low, then pin A will go low, which means that if I have current coming to the power supply down here to my common anode pin, then pin A, segment A should turn on right up here. And if I want to turn B on, then I would have to set pin 3 low. So this schematic is going to be important for you to know when it comes time to hooking up your Arduino to your board. Keep in mind, we may come back and change some of this after we take a look at what it looks like on your printed circuit board, because on your printed circuit board, this could be causing hassles, and you may have to choose, would you rather have a neat, tidy schematic, or would you have a neat, tidy printed circuit board? And quite frankly, if the schematic's a little bit cross line, has a few lines that cross, people can still read it. But if your circuit board has lines that cross, it just won't work. Now, if we were only working with one 7-segment display, I could just hook this anode up to plus 5 volts and all would be good. But later on, we want to add multiple 7-segment displays. So I am going to use an Arduino pin to turn that on. So now, when D8 goes high, that will provide power to right here, and that will turn on the 7-segment display. Now, we do have to keep in mind that there is a current limit on pin D8 of 40 milliamps. So we don't want to draw more than 40 milliamps through there. So if all 8 of these LEDs are on, we could be working that pin a little bit high. You might be better to bump these up to 200 ohm resistors. The 7-segment display will still be nice and bright. 220 ohm resistors, 220 ohm resistors should probably work fine. We'll just leave them saying 100 for now. Resistors are a very analog thing, and you can play around with analog values a fair bit in most of the circuits that you're working on. So right now we have one 7-segment display hooked up on here. Let's take a look at how we would hook it up if we wanted to have two 7-segment displays in here. So if I want to do that, I can either come back here and add another 7-segment display, or I can just come and hit escape a couple times to get out of that mode right there. And I can click right on here and I can go copy, and there it is right there, waiting for me to paste it in right here. And I can paste it in right beneath it. Now, remember what I said, that we're going to be using the same connections, and we're only ever going to have one LED on at a time. So what we're going to do, and let me just move the Arduino up here a little bit so that we get a bit more space for it. Oh, what happened right there? I think I was still in copy mode. I wanted to be in move mode. I should have hit escape once or twice. Let's just move that up right there. Ooh, don't like that line right there. Let's just come in here and okay, I'm just going to delete that and then redraw that line right in there because not particularly liking how that stretched. Let's come down here, and now pin 9 is going to be used to activate. Oh, I hit delete or hit Control Z one too many times. Let's recopy this again. Copy. Just there we go. So we've got two of them in here right now. And let's go ahead and finish adding that into the decimal point down here. There we go. Now that's been routed in there right there. Now that means that sometimes when pin 8 is turned on, I can turn on diode 1 or digit 1, and when pin 9 is turned on, I can turn on digit 2. And because I can turn these separate numbers on one at a time, I can also use all of these resistors to control this one right here. So pin E on this side can actually route up right here and connect right there. So this was pin E on the first digit. It can be pin E on the second digit. And pin D can come up and join right here. Pin C can come up and join right there. Pin B, oh, I think I'm going to run out of space. I needed to leave myself just a little bit more room. So if that's the case and I want to route this nicely, just hit escape a couple times. Draw a box around all of this and move it out. Just 2 clicks right there. Hit escape and then come back up here and straighten out some of these corners. Why does that one not want to straighten out for me nicely? What happens if I grab that line and move it? Oh, really? Are you going to make me go back and redraw all of those? There is no doubt a shorter way to do that. Actually, you know what? That doesn't look so bad up there. Everything's kind of looking in sequence. We might even do that for the ones on the other side and consider that a nice looking display. So let's come in here and finish routing this. So B comes up here and connects to B, and A will come in here and connect up to A. And on this side, F, oh, these ones are going to need a little bit more room. So again, hit escape, come in here, drag those ones out, buy ourselves a little bit of space. And F is going to route up to there. G up to here. And the decimal point to the decimal point for the first digit. So now what we've got is D0 through D7 on the Arduino control what the display shows, and D8 and D9 control which digit is showing in the display. Simple enough. Now we can come down here and we can take this and, you got it, we can add a third digit and I don't know why it thought I wanted to move that. We can copy that. We can add a fourth digit in there, and we can route these so that A comes to A, B goes to B, C to C, D, undo, and it undid more than I wanted. Redo, and D to D, E to E, F. Come out a little bit. You don't want it running over top of those lines right in there. Give yourself a little bit of space. G to G, decimal point to decimal point, and then this analog right here, come up around this way. Come into D10, and here we go down here one more time. And click to make sure it does the corner out here. And that can come up around. Right in there. So now we have a 4-digit, 7-segment display. Each of the pins D8, 9, 10, and 11 are going to control which of the digits is on, and D0 through D7 is going to control which number the digit that's on is displaying. A little later on, we're going to take a look at, well, maybe how could we add some switches over here? Because you probably want to make an on-off switch or something like that. So when we take a look at making our board, remember to leave yourself a little bit of space. We may even leave room on here to put in something like space for a external photo interrupter circuit, so that if you wanted to use this to time cars going down a slot car track or something like that, you could have photo sensors hooked into these pins right here, and as the cars went through and broke the beam, you could display the time from start to finish. But mainly today we're going to be taking a look at the routing, and we've got our circuit board hooked up like that. Yeah, I'm still not 100% happy about those being splayed off at an angle, but we can always come back and tidy that up later. Okay, so let's go ahead and save that. And I think we're ready to start designing the printed circuit board now. So to get to your circuit board, come back to your project, and there you go. You can see the lovely window of that saved right in there, and we're going to add a new PCB. And here we go. I'm going to close this window so I get a little bit bigger space to look at on here. And in fact, I'm going to do the same for over here on this design manager. I can see this a little bit bigger. And there is our Arduino. And there's our display right here. And now what we're going to do is we're going to come in here and we're going to save this. And we've called this 7-segment shield CA. Keep that naming together. And there you go. Okay, let's draw a big box around everybody, and then you have to click on one of the anchors. I see an anchor right down at that corner, and drag it all onto your printed circuit board. Now, you'll recall in some of the previous circuit boards, what we've done for hooking up to our Arduino is we've taken header strips and pushed them through each of these holes. So the Arduino is actually going to be sitting on the back of the circuit board, and we're running pins down through the board so that the board sits on top of the Arduino, just like some of the other boards that we've already made. Now, that means that we want all of these displays to sit on top of the Arduino. So we can pick them up and move them right down here. Now they don't have to fit directly on top of the Arduino, but make sure that they don't interfere, because we can make our board to be a little bit bigger than the Arduino, but make sure that they don't interfere with the spacing for maybe your mounting hole. Actually, you can put them over top of the mounting hole. That doesn't really carry through, but make sure that they don't try not to make them interfere with the USB port right here or the power port right here, if you've got the room to avoid doing that. Okay, they're in there right now. And let's take a look. We've got some resistors to add right here. So we can take the resistors down here. Oh, leave their numbers right on them. They're fine where they are. You got to click on the middle of the resistor to move it. And this one's going to come down here. Now, keep in mind this is looking a little bit awkward because it says that it's got to go all the way over to that pin. Keep in mind that it's also going to this pin, and to this pin down here. All right, so let's take this and rotate it into position so that that lines up pretty nicely and is sitting there coming right off of R4. And then we can bring some of our other resistors down into place and rotate them around a little bit as well. Okay, there we go. So now we've got the resistors onto the board in the right orientation. A huge mess of the air wires down here. Don't panic about the yellow lines just yet. We're going to clean up the yellow lines in a few minutes here. So a couple of things that I note as I'm putting them together, I'm looking at those resistors in the context of the board, and I'm thinking, oh man, I got the resistors too big. And if you're working from previous circuits that we've built, you're probably like, yeah, Jason, you picked the big resistors. We don't need resistors that big for the circuit. So I went out and got my handy vernier calipers and measured the resistors that we are going to be using. And the little 1/4 watt resistors that we have are a different size. So we can change the size of these resistors pretty easily. If you come to the little cross in the middle of it and right click on it right here, and we can come in here and we can just pick the package that we want. And hey, there is our package. We can change the package right now. We had the 0309 with the 12mm spacing. We can probably get away just fine with the 0207. The 7mm spacing is going to be really, really tight on there. But it buys us a couple more millimeters. Let's go with the 020709, and you can see that that changed the size right here. buys us a little bit more space for running the connections right down here and on this side. And you can actually do that for each of them. And O2, O7, O2, O7, and oops, O207, the 9 millimeters. The 9 millimeters just makes it a little bit easier to put them in on that spacing right there. Have I been doing O207? 7? Oh yeah, there's the 9. There's the 7 right there. We can probably do the 7. Let's make them all consistent. It's just a little, you got to bend the leads a little sharper when you put them in. So you're being mean to whoever's going to have to make the circuit board, but you're being nice to yourself as the circuit board designer because you're giving yourself a little bit more room and you're just saying, hey, they can bend those leads on the LED pretty good. I bet they're a good LED bender. And now we can actually take these and position them. No, cancel. We don't need to do that. Cancel. Hit the escape button. We're done. We're done changing that. And we can actually put these in a little nicer and closer together right here. And this is going to make our life go a little bit easier with this package of neatly packed resistors coming together right in here. Now, anytime you change anything on the printed circuit board, it's generally not a good idea to start doing your changes right on the printed circuit board, because where you want to be doing your changes in general is on the schematic. But so long as you've got both your files open and your project open so that the two are saved together, you get something called forward and back annotation. And changes that you make here are back annotated into your schematic. So if we come back and take a look at your schematic now, and I come in here and I click on that part, and where are we right here? And I ask it, what package are you? You can see it says that it's the O207, so it knows that there was a change made. Okay, so that forward and back annotation is really important. And sometimes if you delete a file or save a file the wrong way, you'll get a big yellow and black warning up here saying forward and back annotation has been lost. And that's what that means, is that edits that you do to one part of your design don't show up in the other part of the design. Now, like I was saying, as you start designing your printed circuit board, you sometimes come along and you say, gosh, some things are just going to be a royal pain in the butt to route. And if I take a look at these lines right here, pins 8, 9, 10, and 11, that's going to be really awkward to route over here. Now, I don't have to come all the way over to that side. As you recall, these are coming to the common anodes, so they're turning each of these digits on one after the other. So this is a common anode, and this is a common anode. Right now, I've got it hooked up to this pin. I do have the choice of only hooking it up to that pin, and that might provide me with a little bit better option. It's a shorter run from over here. The other option that I have is I could also use the pins down here to control which segments are turned on. And so long as I wasn't planning on using any analog input devices, that's a perfectly acceptable option to come right up off of here and turn this side on. And that kind of gets you out of the way of the routing of all of these segments coming down inside here. We'll see how that looks as things progress. For right now, I'm going to kind of ignore these, and I'm just going to focus on routing my first 7-segment display right in here and seeing how we can put things together. Now, just in terms of our overall display, since we shrunk the resistors down, I think I can move that in over to here, and we can also put the 7-segment displays, tuck them in a little closer to each other right here. And that lets me maneuver this over maybe a little bit that way. And okay, here we go now. So the way I've got it hooked up on my schematic, and if you've got a second window or a second monitor, you can actually drag this right here and go put that second window on your second monitor. You can print this out so that you've got it sitting on the desk next to you when you're looking at what you're doing right in here. But remember, I said this routed so nicely down here that segment E was hooked up to D0. I come in here and I take a look at it, and well, there's 0. That comes right in there. That comes around over to here. Well, let's see how easily that routes. Maybe it's going to come together. I double click on that. That stands out. I'm going to go route manual. Now, oh, I almost forgot. Before I start doing any manual routing, what I want to do is I've got to come in and I've got to set up my rules so that it knows what we're going to be doing on here. And so I come in and I click on the design rule check, and here are all my rules. So critical that you remember to set this up. And we are going to leave this at 1*16. This is going to give us a top copper layer and a bottom copper layer. Now we're only going to make a single-sided board, but we're going to pretend there is a top copper layer, and we're going to pretend that we have through-plated vias to route in between the two of them. And if you're confused by the term via and through-plated and all that, there is an earlier video in this series that discusses some printed circuit board terms. We're going to leave that on there. We're going to use jumpers on the top layer to jump across the copper on the bottom. Okay, and so we're just going to leave that like that with a little layer of red there and a little layer of red there representing conductive copper spaces. Okay, we're going to give ourselves some clearance right here, and we're going to make sure that we have it when it checks our design, that it gives us at least 15 mils of clearance between everything on here. I know they're listing 6 mil, but now because we are going to have vias on here, we're also going to put 15 milliliters right across the board, and this is for surface mount devices, so I'm not too worried. We're not using them. Okay, distance right in here to the edge of the board, 40 millimeter is probably, or sorry, 40 mil, 40 thousandths of an inch is going to be fine. And let's come in here to our sizes for our traces. Let's set our minimum trace width. I think we can get away with 20 mil. We'll see how that works out. And our annular rings, so this is again the amount of copper that's left over at the top or the bottom. And we now have a top layer, so we're not worried about the pads on the top layer because we're going to use jumpers. We're not soldering to it. On the bottom, it's nice if we can bring that up to 15 milliliters minimum, 25 mil, mil, 25 thou is what the machinist in me wants to call it. Let's just make this a slightly larger percentage of the drill hole, again with the intent of having a bit more copper for students to solder to. And actually, if we drag this off over here and we go apply, you can see that that just got us a little bit more copper. If I just click, I can't click undo right now, but it got me a little bit more copper right on there for those to connect to. All right, our shapes, that's talking about pads, supply, we're not worrying about that. The masks, we're not making a copper mask. There we go, and let's apply those rules. And so when I do a check, it tells me, hey, you've got errors, you've got air wires everywhere. That means they haven't been routed. I'm just going to clear all those errors. We'll come back and we'll clear that up later on. Okay, so now that we've got all that done, we can come back to our design tab and we can start routing again. Okay, so let's do the easy routing first. Ooh, see now that came out in red. Now we do have a top layer, but we don't want to use the top layer unless absolutely necessary. You see that red? That is a warning for you in here. So go back and undo. Let's go down to our bottom layer, which is where all of our copper is going to be, where the easy routing is going to be. And let's go ahead and just put these together. And I remember from my last video, good, I dropped my audio mixer down a little bit, so the little bling sound is hopefully pleasant and not overwhelming. Okay, so each of our resistors is hooked up there. That was a really easy thing to do. Let's see what happens if I see now it for some reason doesn't want to route through that hole, which I can see why they offer up the choice of having an Arduino board with no holes on it, because really it shouldn't matter whether or not I route over top of that hole or not. And my design rule check is just preventing me from routing over top of that existing hole. It thinks that this is the only space that I've got for my board. And you know what? That's actually kind of a neat feature. I respect that. It's just bothering me right now. So let's come down right in here. And what I'd like to do is come around that hole and come into right here, and we'll route down over to here, and that one's routed right in there. This one's going to come right down in here, and I'm clicking on it every now and then to try and get it to stay together, and it's going to come in and click right in here. This one's going to want to come down, and not quite enough space right there. So I can't really go in between these pads safely. That's going to create a big hassle for my students, and they'll probably screw it up. And if they screw it up, then I'm going to be the one who's not happy. So I'm going to stop routing for a second. I'm going to pick up all of these, and I'm just going to give myself a little bit more space over here. And again, I'm going to try not to put them right over top of any of the other components that we've got. I think I might be able to get away with that if I'm cautious about how I come right around in here. Now you'll notice when I move things that I do have to come back and tidy up this corner right here, shrink that in a little bit. Actually, what I should have done was just come in here and right clicked, told it I wanted the miter, and mitered that corner. And now I can pull that out right there. In fact, while I'm here, well, I'll miter those corners a little bit later on. Let's pull that out there. That's going to give me a little bit more room for routing things into this side over here. Let's see what I can do with my next one right here. And come to route. And that one wants to come down inside of here. And we've got another one that's going to come around down to this end. Now, it looks like these are getting just a minute, hit escape. I was just coming in here to a break out of routing. Just wanted to move that over a little bit and see if I can move that over a little bit. There we go. I'm manually placing this over top of the hole. It's going to tell me that I've got an error there. But when I go to make this board, that's not going to be an error at all because I'm not going to replicate that hole onto my board. That's the mounting hole on the Arduino. And in fact, we don't really have to worry about that. So I'm just going to manually move that right over there. Move that right over there. And you can see those hash marks showing up. That's warning me, hey, you've got an error right there, you fool. What are you doing? But I know what I'm doing. And we can ignore that error right there because we're not going to replicate that hole. And what that lets us do is it lets us route this one right in here. Oh, hold on, it only wants to go to that hole. So this, as I recall, was our decimal point. And our decimal point, it says it's hooked up to that decimal point, hooked up to that decimal point. And if I follow that air wire back here, it says this is the one that wants to come down and connect to the decimal point. That's going to be a tricky one to route. Let's try a few other things and see what solutions we can come up with. Okay. Where does this one want to go? This one looks easy. Let's do that one. Oh, now that decimal point, getting it right down to there isn't going to be fun. Maybe there's another solution that we can come up with. Can it come back around underneath this way and come down in through there? Possibly if I move hit escape and stop routing for a second. I want that decimal point to be able to sneak around the inside. Let's move these over just a little bit. I don't want to go so far that I thrash anything right in here. Let's create a little bit of space by moving that down like so, down like so. And now this one, if I come along and I route that, can come back this way underneath here. And let's see if I can bring it to, I don't like either of those places. If I hold down, was it the Alt key? There we go. That gets me the fine adjust. And then I can bring that to right in here. And that gets me routed right to in there. Okay, that's not looking so bad. We've got one digit almost working. Now, again, this 8 to get down here and power, it's going to be a little bit of a pain. And we've got a few options on the power. I'm just going to leave the power pins alone for a minute. What I do have to do is I have to get these connections right here to connect over to right here, because this is connected to this one right here, and this is connected to this one. Now, some of that is pretty easy to do. So if I take this and come to right here, that comes in there very nicely. And this one, if I come in right here, comes over to that one very nicely. And this one right here, if I come up right over to here, connects in to that one fairly nicely. And now my routing options are starting to get a bit more awkward, because this one needs to somehow get over to right here. And that looks like it's going to be a real pain in the butt. And this one right here looks like it needs to get out and come around. Now I might be able to do one of these by taking this resistor right here, moving it over a notch, moving this back up a notch right here, and then this one right here could break free and come around this side, but that doesn't get it to right there. Starting to run into some problems here. Went back one step too far. So those ones are coming together really nicely. We need a way to break some of these free and jump them out over the top and make them work. Now, the really cheap solution and the ugly way to do that is to go back to your schematic, and instead of just joining them with nets, join them with resistors. Because if I had a resistor connecting this pad to this pad, then it would be really easy. My resistor would come over on the top and it would be able to jump right up and over top, and I'd be able to make that connection. But we don't want a resistor in there, so what do? You call it a 0 ohm resistor. And when you think about it, what is a 0 ohm resistor? A 0 ohm resistor is simply a piece of wire. So if you wanted to run a jumper wire on the top layer, you could fake it, throw in a resistor, call it a 0 ohm resistor, and all it is a piece of wire. So if you ever see a printed circuit board design where somebody's got a 0 ohm resistor in there and you're wondering, what the heck is a 0 ohm resistor, then don't worry too much. That 0 ohm resistor is merely a piece of wire, and it's their way of putting a jumper in. We're going to use a slightly different way to route the jumpers into there. So now we're ready to try putting some vias into our board and using jumpers to fake the top layer. So what we're going to try to do is we're going to try to connect this pad right here to this pad over here. And to do that, we're going to come up right here. We're going to put a via in right here so that we can swap to the top layer of the board, come over right here, put a via right here, and then swap back to the bottom layer of the board so that when it comes time to build the board, we can just make a wire come right along here and do that jump for us. Now, if we were having this board commercially produced for us at a factory that could do through-hole plating, what we do is we just draw a line in the top layer right like this that would come and connect to that and be no problem at all. But unless you're going to get the board commercially manufactured, kind of hard to do that in your shop. It can be done, but you don't get the through-hole plating on there, so then you've got to figure out a way to solder the top side and the bottom side of the pin. More hassle than it's worth. I'm going to show you how to quickly do it with some jumpers in here, and you'll just use strips of wire to do it. So the first thing we're going to have to do is give ourselves a little bit of space by moving this piece up, and now that'll be far enough for now. It's just out of the way so we can come out here and put a via in right here. Then we're going to come over and going to join it right here. In order to do this, you are going to have to use the middle button of your mouse. So, oops, I've been practicing this. Make sure you're on the bottom layer. We're going to start on the bottom layer. You're already on the bottom layer, but okay, so start right here and just click, go to route, and your routing menu should come right up on here, and tell it you're going to route from right here. And now it's giving you all the possible options. You see it's not letting me route over top of there, which is good. And what I'm going to do is I'm going to come up to here. I'm going to find some empty space. Now before I get there, hit the middle button of your mouse once, and you can see that now I have a via available right in here, and I can figure out where I want to put it. And this one I'm going to keep it tucked down. I'm going to come up a little bit right here. I'm going to put it in right here. Now you'll notice that it's switched over and it's red. Remember I said red is bad, that's our warning sign. Well, not if you're intentionally trying to be on the top layer. And we're going to hit that middle mouse button again to swap layers. And now it's like, where do you want the via? Well, I want the via to be right here. And now that's joined those two connections right there. And you can see if you zoom in on it that this is net 8 all the way along here. And this jumper that comes across right here is net 8. And so these two pins are hooked together right now, which is exactly what we wanted. Very handy being able to put those jumpers in and come right across the board. And because we came out here to create a new via, we're able to jump right across there. Now your via might not be the same size as mine. In fact, yours might be too tiny for a student to actually drill and to solder. And that's because while I was practicing, I came in here and in my design rule check, okay, so right back up here when we set the DRC, I'd forgotten to tell you to change the annular ring. So go into DRC, come back to annular ring, and for your vias, okay, right in here, set your minimum on your outer layers. Okay, we're not dealing with inner layers on your board yet. That's definitely one that you get done commercially. But on the outer ring, we've got 20 thou and set the maximum up to 25 thou. And what that'll do is that will increase the diameter of your vias right here so that you're able to drill a hole and still have an annular ring, a little bit of copper left for people to solder to. Okay, then just click apply right on there and you can close that window and you should see your vias come out to be that size as well. Okay, now before I want to route the next one, I want to be able to join this one right here to this one right over here. I don't see, I guess technically you could come back around here, give yourself a bit more space here and pull it in right to there, that might be a preferable option to doing the jumper. I try to avoid jumpers whenever possible because they are additional work for whoever has to do them. You've got to make the wire, strip the wire. You lose some of the benefits of going to a printed circuit board. So I try to always keep the jumpers down to the absolute minimum number. But let's create a little bit more space. I think we want to move this up a little bit more. And so I'll move that right up to there. That lets me move. Oh, I don't want to bend that. I'm just going to see if I can move that via up right there. And just to create space for the next one to come in right here, and this via right here, see if I can click on that via, and then it's giving me a hard time picking it up. There we go. I'm just going to move that into right there. Move that line right in there, and pick that via up. Make sure it's nice and bright green because that's the one that I want, and I want to move that to right there. It is just being fussy on how it's automatically routing that for me. There we go. I'll leave that right there. As soon as you get the vias in there, life can get a little bit fussy on how it routes. Let's put that back down in there. You can see that little blue sign in there comes up, and that's a warning sign in that hashtag that I've probably got an error of some kind, and I do. Can I move? It's the via that I want to move over right here, and I'm just having a hard time gripping it and moving it without moving everything else. And because right down there, now I've got a warning right down in there. So I'll move that over right there, and I'll call it done for right now. I may come back and straighten that out a little bit later on. But anyway, let's try routing. And again, come into design if you've been working in DRC there for a moment. And now this one needs to come over here and connect to right here. So I'm gonna make sure I start in the bottom layer. Always start and finish in your bottom layer for what we're doing right here with the jumpers. Come up right in about right here. And middle button to get a via. Pick a nice place to put that via again. You can put it in pretty close right there. Bring it in right over here, and middle button to get the via, and that's net 5, and that's joined together right there. And now we'll have two wires sitting on top of our board, joining those together and jumping over top of that routing down right underneath right there. Okay, now we've got to come down and do the bottom right in here. We managed to come across and route those two in right there. And we should probably be able to find a sneaky way to get this one right here. Again, let me make sure I'm on the bottom layer. Always watch which layer that you're on. I should be able to come along and route from right here. And as I get close to that one, you can see, yes, it knows that it wants to come in right here. Now I'm going to leave myself a little bit of space, maybe not that much space. Want to bring it in about like that. So I've got some space in here for the inner two to come across and do their via thing. And just to make that a little bit easier to make those connections, I am going to come in here and miter this right now. And what I'm doing by mitering that is I'm actually thinking ahead to later on if I want to connect to right here. This pad is now very effectively trapped and unable to get a signal from anywhere. So if I want to use that one, this one's also somewhat trapped up here. I may need to be able to put a via in right here and jump it out to somewhere else. Okay, let's take a look right in here. And now I will say time to add some vias and jumpers. And so start on the bottom layer and route from right here. Oh, select the route from right here. Come down right here, middle mouse button, remember to get the via. Put the via into a suitable location. Come across to right here, middle mouse button to get your via. Again, you can see these are stamped with net2 and join it together right there. Why didn't it go bing? There we go. I just had to finish off with a little bit of copper on the bottom to make sure that joined together right in there. Okay, and then I want to route net3 together. This is net3 right in here. I'm on the bottom layer. I start off in blue. I come out here. Middle mouse button to get the via. Put the via right. Middle mouse button to get the via. I'll click right there. I'll come over to this side and middle mouse button for the via. And I will join that in. I might have to press the regular, the left mouse button again to just make it go bing. Make sure you hear that bing at the end. That's your little reward for connecting the net together. Okay, so that's got us with two of the LEDs hooked up aside from their power. You should be able to whip through and connect up the next two of the 7-segment displays. Let's take a look at how that goes together. Okay, so that gets the board cleaned up a little bit, and it's got all our A, B, C, D, E, F, G, and decimal point lines connected to each other. All of these resistors are busy doing something, and you should be able to follow that line and see that it's connected to 1, 2, 3, and 4 different displays, and you could carry that on if you needed more decimal points. And you should be able to take a look at any one of these. This pin comes down, resistor comes around right here. It's connected to 1, 2, 3, and 4. Okay, now one of the things that you do have to keep in mind about using the jumpers and putting them up on the top layer is because they aren't exactly on the top layer. They are a physical piece of wire. You can't always run them underneath other components. And although technically you can cross them. That's one advantage of using insulated wire. We try not to do that. We try to keep nice straight runs. So if you ever did decide to have this commercially made, you could do it. With a commercially made board, because it would just be a copper trace and it would be protected likely by a solder mask, you could have ran these connections on the top layer right in underneath here and ran them underneath the components. There's definitely some advantages to having someone make the board for you and having you do through-hole plating and giving you nice properly indexed top and bottom layers. Okay, let's wrap this up by taking a look at how we can hook these up over to these different pins right on here. Now, keep in mind we can use the top side or the bottom side because these two are both internally connected within the chip. We may have to go back to the schematic and change it if we want to connect to this side. Right here, I see a bunch of nasty routing. If I try to come out right here, I mean, I could run one big long continuous jumper on the top layer all up and around here and right into there, but we try to avoid big long continuous jumpers. It's nice to have just one short straight one anytime you can do it. And you can see down here, I actually managed to avoid putting in a couple of jumpers by coming down and connecting them in over here. Um, Net benefit of that might be slim because, of course, now these ones need to come up here and connect right to here. Well, knowing what we know about the boards and knowing that these two are essentially the same, we could route underneath the board right from here to here and come out right here, go to the top layer, jump over to the top, come back to the bottom, come back, route it into there without too much problem. This one could come out right here, route underneath those two, jump over those three, and that one's going to come back to right there without too much problem. These ones are a little bit tighter spacing, so we'll see what we can do to get into them. I think we've still got some solutions that we might be able to pull out and make them work. We might have to space a few things around on our board to make it work. This is the most complex board I've asked you to route so far, which is why I'm walking you through it to the end with this two-layer routing going on. It does require a little bit of an eye for figuring out what is going to be happening here. And, you know, I just think this is going to be simpler if we don't even bother routing underneath the board and coming up right here. Let's just change certainly D4 and D3 for right now so we connect to the other common anode on there. So just come back to your schematic right here. And for D4 and D3, you can see that we've connected right here. So just come in here, select this line right here, and press the delete key. That deletes right there. And then come in here and connect your route key and come down one more connection and route in on that side. Come down here, press the delete key, and come down one click. Connect right in there. Now you'll notice on the printed circuit board, I've gone back and I've mitered a lot of the corners. Generally on a schematic, try to keep the corners square if you can. Simple is better on the schematic. Somebody has to read that. On the printed circuit board, keep in mind, that's got to be a practical solution. It's not telling a story, it's just doing what it does. Okay, now if we've done that right, let's just save that to make sure that those changes are saved. And really, I should be saving these as I go along in here. Let's a little brief pause while it uploads everything to the cloud right there. I don't think I clicked on close, but I'm glad I've been saving everything and everything's been auto-saving. That wasn't supposed to happen. I always get that warning message. Recovery files were created. Click a file to open or delete it. I think we will open that one. And we will open this one. As a new version, do you want to load the latest version? Yes. And let's hope that it recovered all the correct versions. This one is looking good. This one has all of my latest in there. Let's close those windows so we can see it a bit bigger. This has all the last changes that I made. All of the jumpers are in there. And let's take a look at our schematic down here. And the beauty of having a cloud automatically save things, these changes are also in right here. I'm just going to try hitting that save button again. That one says it's already saved. This one, let's save that. Oh, I see while it saves that, it saves both of those files for me. And now everything is updated to the latest version on here. There's my board, and here's my schematic. The schematic's been updated, and now when I come back to the board, you can see that now we're connected onto these pins right here. So, weird. Didn't need that to happen right now, but it's nice to know that even if Fusion 360 crashes, sometimes it looks like it saves your files for you. May have been something that I did. No harm, no foul. All right, let's connect this one right here. So we're going to start on the bottom layer, and because that's where all our copper is, we're going to do some routing. Going to come right in here. Middle button to get me that via. Via goes in right there. I'm going to jump right over top, right up to here. And that seems like a reasonable place to put in some copper. Come over right here and wrote that in right there. That one is now connected and it's happy. So I'm on the bottom layer again. So I am going to route from right here, going to come underneath that top layer. Oh, it's telling me I don't quite have enough space to get in there. So, okay, I'll see, it'll let me come over here and it'll let me put a via in right there because there's just that little bit more space. Hold down the Alt key and see, no, it's just not giving me enough space. Remember those design rules I set in place won't let me put it in a place where it can't go. So let me just hit escape. I'm not going to route that for a moment. I'm not going to fight it. I'm just going to come in right here, stop my routing, move this up a little bit. Going to move that via up a little bit. I'm going to come in here and I am just going to put a split into that line right there. Say okay. I'm going to come in here, move that up a little bit, and I'm going to come in here and I'm going to put a split into that line right there. I'm just going to move. Oh, I guess I didn't have to. That's already up a little bit, so that's fine. And I just bought myself a bit more space in there. I'll come back and I'll just miter that corner and that corner just so it looks nice and pretty. Okay, and now we've got a little bit more space in there. So when it comes time to route this one right here, I can start on the bottom layer, come underneath those two, middle button to get my via, my next via. Oh, why not make it line up with that one right there just to be pretty? And then come in right here and over to right there. So those two are jumpered nicely into place. Now, what am I going to do for these two bottom ones all the way down over here? That looks a long, long way away. So it might be easier to change this one so it comes into here. I could do copper underneath here, and then I could do top layer. Don't want to have my top layers cross right there. So could I bring this side down a little bit? Well, I still want to get that side out right there. Trying to think how I can keep this to an absolute minimum number of jumpers, because jumpers are extra work for the person that's got to build the board. And they're also an extra chance for something to go wrong. So let's take a look. If this came down out here, we could go. No, this one's probably the easiest one to get out of. How can we create a little bit of space right in here if this via moved over? Tough routing problem right in there. Let's do this one first and get that one out of the way, because I think we can solve this one by bringing, no, cancel. I don't want to route anything there. I want to bring that via down a little bit so those two are right next to each other. Just to keep my vias nice and straight, this one can come down right to there. That actually buys me place to put a via in right here. Okay, I think I see a solution where this is all going to route out okay. So let's change these two over to the top layer, just like we did a moment ago. So we come back to our schematic and just click on that one right there. We'll delete that and we'll delete that. And then we'll just change our nets. So they come right over here and they come right over here. Now you can see we're going back and editing the schematic to make the schematic a little easier to design on the board without damaging the integrity of the schematic. So that's perfectly fine. We want to keep the schematic all in one piece. And it's pretty common actually when you start routing your board, because really in software on your microcontroller, you can change which pin does which. So D0 doesn't have to go to E. That's entirely flexible to change in software most of the time. So don't panic too much if you're routing a board sometime and you're like, nothing will route. Come back and play around with it and be creative. There's usually a couple of different ways you can go about solving your problem. Okay, so if I come right in here, let's take this and just going to move that down a little bit right there and move that down a little bit right there. I might move that one. I'm just going to hold down the Alt key so I can do a bit of fine adjust. What I'm trying to do right there is just keep some nice spacing in between those lines. It just makes it easier to etch, less likely that something's going to go wrong in there when it comes time for a student to assemble it or put it together. Okay, now we're going to route underneath here, and we're going to jump up and over, put a via in there, and we should be good to go. So we're on the bottom layer, let's route, and we're going to come out underneath there. Is it going to give us room? once. It says you don't have quite enough room to tuck a via in right there. So I'm just going to escape from this and gonna play with a few little settings in here to try and buy myself a bit more room. Holding down the Alt key, let me just a little bit of a lag on that. Shuffle that right into there. Slide that right down into there so that comes and slides right around there. We'll just keep that nice and lined up. And that probably bought me enough room to come in here and route from right here underneath. I can put my via right there now. Take my jumper, and this jumper, I'm gonna put a small bend in it. Actually, I'm gonna put a fair bend in it right like that, just to give myself some additional room so that I can finagle that pin 8 in there. There we go. And we'll come in here and finish that into pin 9. Pin 8 is being nasty, but if we create a bit of space right in here, I might be able to get underneath here, put a via right here, and then route a 2-bend jumper up there. I really don't like doing a 2-bend jumper, but I can't route through the resistors because they're also on the top layer. And yeah, 2-bend jumpers work. Everything else on here is nice and straight and easy to do. So let's go ahead and give that a shot. So I'm just gonna move this over and see if I can create a little bit of space for myself in here. I think I can come in here and move that up a notch. So lets me move that up a notch. Lets me move that up a notch, which should give me space right there for a via. Okay, and so let's come along in here and route this underneath the board right here, and we'll come up in here. That looks like a spot where we could have it. And then I'm going to bring that up in here, up in here, up in here, and tuck in underneath. And for some reason, I'm not clicking right on there. Should tidy that up a bit. That's looking really ugly. Okay, that'll do. There's enough space. Alrighty. So now if I can follow that one through, that one comes down here, switches up to the top layer, 1 bend, 2 bend, 3 bend. Oh, more complex than I wanted it to be, but I had to get around those resistors. And it's all okay because that, although it crosses over the other signals, it's on the top layer, comes to a via down here, which allows me to transfer back to the bottom of the board, and then that routes right underneath there. I think I've got my entire 7-segment display hooked up, and we could build this display. Now, ideally, it would be a little bit more compact, so I'd have room to put a couple of switches or a couple of jumpers right in here to go out and power up some external devices. And I think I can see some room in here. I was leaving space right around here to hook up some other devices. I could clean that up, move those in a little bit, and I could put a couple of small switches in here or just a couple of header strips so that I could take an external device and hook it in here and have some on-off switches for turning my Arduino on and off. The other thing you can do, of course, is you can use what's called a stacking header so that you can still connect to each of these pins from the top layer of the board, as well as have the Arduino plug in underneath. But there you go. This is a shield for an Arduino. Now, before we finish up, we've got a few things to do, the final touches. So first of all, let's come to our rules, do our design rule check, and click on design rule check and go check. And oh, it's telling us we have an air wire left somewhere right in here. So this is net 8, this is net 8, and oh, that little yellow wire in there, for some reason it didn't connect, but you can see right on here that we're all connected. Those pads are down on the copper layer, and they're connected by that piece of copper. So that is probably not a real error that we need to worry about. If I was sending it out for commercial manufacturing, I'd take a look at it. Now, your dimension errors right in here are saying that, hey, on the dimension layer, we've got copper going somewhere where the dimensions say that there should be a hole. We're actually, as we said earlier, ignoring that hole, and you can see that that's aligning it all. I'm just going to clear all those errors, and there we go. We're good to go. But when you do that design rule check, it is going to check to make sure that you've got appropriate clearances, and it'll let you know if you don't. Just a certain part of me really feels the urge to miter that. And I should probably be able to bring it up so it's aligned right in there. There's probably another little corner or something in there that I'm going to look at later and say, gee, I wish I'd tidied that up a little bit. Final thing to do is, of course, come to Document, and under Draw, find your text. And on your bottom copper layer, 7 seg CA. Always mark the board as your own. I have nasty things to say about the fact that when I press OK, it doesn't let me put in the text. 7 seg CA. There's a little corner of the board that has space. Okay, I'm just going to save that. And now when I go to print this one to show it to someone, normally I would use my layers, and I would only show the bottom layers. Okay, and that is what I would use for making the printed circuit board in the shop. Okay, I just want those, just want the copper layers and the pads right on there. That's what I'll use to do my etching and my drilling and everything like that. But this time, just so I can see the entire setup, just leave all the standard layers turned on, and then you can go ahead and print that out to a PDF file. And actually, this time, instead of printing it black, I'll get you to leave it with the colors turned on so I can see what you've put on the top layer and what's on the bottom layer, and we don't get them all confused. Again, for manufacturing it in the shop, your toner transfer layer would be solid black, and it would only be the bottom layer. If you wanted to print a top documentation layer, you can also do that and mirror it and put it on, and that would show you where all your jumpers are going to go. There's more jumpers in this board than I would like. Let's see, I've got 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 jumpers in there, I think. Maybe it's possible by changing the way that you've hooked up the schematic, or by changing how you've arranged your resistors, maybe it's possible to eliminate some of those and still have a neatly routed board. I'll leave it to your creative imagination to come up with a better routing. Again, before we wrap up, let's come over to our schematic. And while I was putting it together, I missed the critical part of saying what it was. So I'm going to come in here, and again, We've got a bit more space for text on this. 7 segment 4-digit display. I should say common anode. Oh, doesn't really matter. That becomes, well, it is apparent when you look at it, but may as well leave yourself a note. Put your name on it and your date. And slap that in here. I'm just going to tidy that up a little bit. That's going to look a bit better. Increase my size. Displays a bit more prominently. And there we go. And again, you can print that one out, then print it in color. But most importantly, make sure you save it. And also, when you come to your project file, make sure you save your project file before you shut down. So they're all there waiting for you in the event that your program crashes on you. Weird, don't know why that happened, but it's not so bad if you bounce back right away. Next week, we'll take a look at some of the programming for this in our 4010 course.